Thanks. So hi, everyone. My name is Veena Krish, and I'm a second-year PhD student at Stony Brook in computer science. I volunteered to give this workshop on data science, and I'm pretty excited. I was around for HackHealth last year, and the quality of projects just sort of blew me away. So I'm excited to see what you guys will come up with this year. This workshop is titled Data Science with Biomarkers. It's going to be a pretty basic sort of introduction to some common data science techniques and tools in Python using scikit-learn. And at the end, I'll go over some visualization tips using Bokeh. If any of you are just watching and waiting right now, most of this workshop is going to just be a walkthrough of a Jupyter notebook, and I'm doing this through Kaggle kernels, so you should all be able to access the notebook, make a copy of it, and start running. I have a couple slides before I'll start this, so I'll show this link again. But if you're bored, see if you can access this. And don't worry, I'll show this again and sort of walk through how to launch it and copy it and start your own kernel. And this is my rough idea of the schedule for the next hour or so. I know that there's probably a variety of existing skills and interests in this audience, and so some of you may be looking for just a very basic introduction to data science. Some of you may be looking for mentions of visualization tools or techniques that you could use with over the next couple of days. And so I plan to just give a quick overview and then switch to the Kaggle Jupyter notebook, look at some exploratory analysis with a particular data set that I've chosen that involves biomarkers. And then we'll start building some classifiers and then iterating, refining the data sets, making these models a little bit more complex. And then I'll end showing some sort of what I consider like a pretty straightforward way of developing interactive visualizations that it could be useful for the hackathon if you're interested in kind of building a concrete product or app at the end of this. And hopefully I'll pace this right to give you all some time to follow along with the notebooks and explore a little bit of your own. So just a quick overview. If you're here, you probably already know, what is data science, what is a biomarker. But as an overview, the phrase data science really became popular maybe 10 years ago, largely in response to the production and easy access to huge amounts of data, and applications to healthcare are pretty interesting and still an active area of both research and data science, as well as medical research and active development. A biomarker in particular, I sort of use that term in the title of this workshop, just as a kind of a catch-all. A biomarker is a measurable biological variable that is an indicator of the presence or severity of disease. And so these can be measurements from blood or tissue samples, molecular analyses, presence of particular segments of DNA, etc. They can also be other measured indicators of biological status, like patient's temperature or amount of a certain certain chemical. And largely these are used to track disease, to develop therapy. The particular example that I thought would be interesting for today's workshop is this Women in Data Science Datathon topic from last year. It's an ICU mortality prediction, and given a tabular data set, the goal of this challenge was to predict patient survival from the first 24 hours of ICU care. And I came across this data set because it was also a PhysioNet challenge. So PhysioNet is a pretty vast bank of data and tools full of real physiological data. It's been pretty well maintained for the past decade or so. And I use this actively in my own research. And they in addition to just providing certain data sets, they every year release a challenge. The one that I chose from a couple of years ago is also a Datathon Women in Data Science challenge. And let me just give you an idea of what this is. It's tabular data of a couple, about 100,000 instances of ICU visits over the course of a year. And they sort of invite Women in Data Science invites people to participate in these data science challenges every year. This was from last year, so it's closed. You can't submit your new classifiers for this currently, but they do have one for 2021, which if you're looking for data sets or interesting challenges or ideas, that could be a source of inspiration for this weekend. Let me go back to my slides. So for the rest of today, or for the rest of the hour, I'm going to show you how to download this data set, work through it, and I hope that sort of the key takeaways from this are going to involve tips for data imputation, the data munging in general, cross-validation, how to properly validate classifiers or models that you train. 3, how to properly score how well your classifier is doing, sort of goes hand in hand with cross-validation, the evaluation side of training a model. And then I'll end with some visualization techniques, using Bokeh to develop interactive visualizations that you can maybe integrate into an app. So I said I'd share this again. This is the public URL for this Kaggle Jupyter notebook, Kaggle kernel that I have. Hopefully all of you can see this. If you log in from a guest account without signing into Kaggle, you should see this kind of screen. And if you hit copy and edit, that should launch your own Jupyter notebook, and it'll take a second to download the data. One thing to note is that I think the kernel shuts down after 15 minutes if you are not logged in. So if you are planning on just opening this and leaving it be for 15 minutes, you may have to kind of reload and you may lose your data. I would advise logging in if you do have a Kaggle account. But hopefully all of you are able to see this. This is what it should look like from the top. And then I've also got the link to the slides here, if you want any of the information that's in there. So I'll give it a minute. If anyone has any trouble accessing this, maybe there's like a way to comment. Hopefully Cynthia can let me know if anyone's mentioning any problems.
Can you show the link again?
Yeah. Why don't I fix this? I'll fix this font. This might be a little hard to. Oh, it's a 0. This is the same thing. It's just the tiny URLs isn't working. Oh, maybe it's worth saying, so while you're getting this set up, maybe it's worth just mentioning what Kaggle is. If you're unfamiliar, Kaggle's a pretty popular site for hosting data science, data analytics challenges. It's now widely used for classwork as well. So a lot of you who are interested in taking data science or machine learning classes will likely interact with Kaggle in some way. And the first machine learning class that I took, had us participate in a couple of Kaggle challenges as part of our homework assignments. And they have they not only host challenges, but they also have a pretty thorough and informative set of courses of their own that are bringing you up to speed on not just data science topics, but Python and how to make the most use of Pandas and NumPy, visualization. Once you sort of get used to Kaggle, you'll probably notice that a lot of the data sets that are uploaded by people are pretty well processed. Like they're pretty clean. They may have missing data, and there may be the data may be noisy, but generally you'll always get a single CSV file with tabular data, and they don't require too much additional processing. So it's a great site for learning and practicing some skills, especially before interviews. If you need to brush up on just how do I load a CSV file of data with Pandas again? You haven't done it in a little while. Oh, companies also post their own challenges, where if you compete and you get in like the top couple of places with a substantial, they offer substantial awards. So hopefully that's long enough that everyone has been able to. Yeah, thanks. I see you posted it on Discord. Let me start this session because I was idle for a little while. This first block is provided by Kaggle as boilerplate, and it's all I'm doing is importing NumPy and Pandas, which, if you're familiar with Python and sort of basic data processing, are the two predominant libraries for handling data. They're useful for matrix or tabular data, and so Pandas is a library for handling data frames, where you've got instances of your examples as rows, and then the columns or the features of the data set as columns. So let's take a look at this data. I'm also importing a couple of plotting libraries, and I'll mention that in later on when we get to that. So I am reading in this single CSV of data as a Pandas data frame. I'm calling it df-raw, and you can see there's about 100,000 instances and about 186 columns. And so usually the instances are called instances, examples, samples, data points. The columns are often referred to as features. So if you see that the terminology and you're not clear, which is which, examples and features. Let's sort of peek at the first couple of rows to just see what this looks like. And there's a kind of common refrain in data science work that most of your time, like 80% of your time, spent on a data science project is really involves data processing, data munging, like making sure that the data that you have is meaningful, nothing's missing, that the actual model training isn't going to be that much of what I'm going to show here. One thing I wanted to do is let me put this side by side. Put the schedule here. And then let me make this a smaller part of the screen. And just because this isn't that wide to begin with, and anyone who's sort of passively or paying attention here can keep an eye on the schedule and join if they want for visualization, etc. So once I've loaded this in, a common useful task are to get an idea of the types of data that are in each of these columns. So they're ins, floats, as well as objects, and generally, like NumPy objects are usually strings. These are probably categorical data that will have to be processed somehow before loading them into a model. I'm also calling describe to show mean, standard deviations, etc. for numerical columns, get an idea of really what this data is. And so you can start to see that this challenge involves predicting this feature, hospital death, from these other pieces of information, age, BMI, and then a variety of biomarkers, heart rate, hematocrit, sodium levels, etc. And so I'm going to spend the next couple of minutes sort of going through some data processing. It's not the most like flashy or interesting part of this, but it's critical for preparing your data for modeling. And so one pretty important step is to handle missing data. So this is-NA is just showing the number of samples for which there is no entry for each of these features. And you can see some of these are complete, ICU IDs, etc. And some of these have very little data for any of the entries. And in a second, I'll talk a little bit about different ways to impute data. But first, let's just kind of get an overall understanding of this data set. That's sort of another interesting thing to do is look at what features are categorical. So which of these object data types, which of these are object data types, as I mentioned earlier, and that unique to see what the unique values in these categorical data sets are. ethnicity. You can sort of play around with this. And I'm kind of going through this a little fast, but and you can reference this data set if you're unsure. This notebook if, like, in the future you're unsure of what functions to use for different things. But I'm just kind of showing how to get an overall picture of this data. And lastly, kind of one important thing to keep in mind is the relative values of the classes in this data set. So the class that we're trying to predict is hospital death, and though this class isn't equally balanced in this data set, there's only about less than 10% of this data set has a true class, and this is important to keep in mind while building something, because you want to make sure that you aren't building a model that is just always going to predict false. Hopefully that wasn't too fast, and I know it was kind of just a quick roll through of a couple of things you could look at to get an idea of the data set. Next, I'm going to launch into how to use scikit-learn to build a basic model that, and first, what's the most basic model that we can train with no effort, sort of that fits within the time limit of this workshop. And so ideally, we wouldn't launch directly into this because we know that there are quite a few problems with this data already, that there are real string valued features, as well as plenty of missing data. But I'll show you how this works using scikit-learn, and then we'll go back and sort of iterate and make this a little bit better. And I mentioned scikit-learn without introducing it, but scikit-learn is also a pretty popular, almost standard library in Python for data and analytics, data science. It's pretty well documented and widely used, and you can use it for classification tasks, but also regression, clustering, visualizations, etc. And this standard Python library, so like a conda install sklearn or pip install sklearn is all you need to load up. So from this library, I'm importing two things. One, a logistic regression classifier. It's my slides here. Let me see if I can make this bigger. So a logistic regression is a pretty standard model for handling binary classification tasks, as opposed to regular linear regression, where your output y is a matrix multiplication of your inputs and some weight vector that, and the weight vector is what gets learned by fitting this regression to the problem. A logistic model takes the form of this kind of sigmoid, which fits this problem nicely, because the output of our classifier is binary. It's always going to be either 0 or 1. And what gets the weights, the B vector, is going to get learned as we fit this model to fit a logistic regression model to this data. But the output class gets decided based off of a threshold and a logistic transformation of the products of weights and the inputs. And that's just to sort of give you an overview of what this model is. People refer to data science as an interdisciplinary field because it does, you do want to understand the how the particular models you're using work, the assumptions behind them, what cases, a model is going to sort of give nonsensical outputs, and what places is it not going to converge on time. And that kind of knowledge comes from linear algebra and mathematics and statistics. And so I'm going to show you how to just easily load a model and fit it, but keep in mind that there's that understanding the linear algebra behind this does help in improving. So hopefully everyone is still going along with this. I'm going to define the columns that I want as input, basically everything in that data set except for the actual output and this unique ID, the encounter ID. Here's the target Y. What's the easiest thing to do to format this data in a way that I can actually train a classifier? And to start off, let's start just dropping all of the columns for which there is any unavailable data, because currently we don't have a way to encode or handle NaN data, especially for those columns where almost everything is missing. So let's ignore that for now. And you can see out of all of those columns, only 9 remained. Let me just show you what that is. Patient ID, hospital ID. These sort of make sense because these IDs are things that should be, are probably input with the patient in the first place, and so they're unlikely to be missing. But you can see there's some pretty important features like, say, age, information about disease, or particular alarming biomarkers that aren't represented in this. So this initial classifier is not going to be very good. The second thing, of course, is handling those string variables. I'm going to one-hot encode them, which just means that for every unique string value, every unique string value in a column gets turned into its own feature. And wherever for that string, every instance of that string is now encoded by a 1 in that new column that represents that string. So in for ICU type, where previously we had one ICU type column, and then this first row would be CTICU, and the second and third rows would have surgical ICU. We're just replacing those values with binary vectors. I'm going to split this data set into training and testing. Ideally, do this multiple times, but the reason why this is called cross validation. The reason why you do this is because it's possible that you will develop a model that almost perfectly explains some given training set that you have, almost exactly. But once you try to apply it to new data, it fails to accurately represent, the true data distribution. People refer to this as a problem of generalization, or overfitting. It's possible to, develop a really highly complex model that really accurately describes one small data set that you have, but you can't use it to say anything about new data. So I'm going to randomly splitting the data allows us to develop a model on one set and then see how well it performs on the withheld set. Using scikit-learn logistic regression to fit and then score this. Score here refers to accuracy, which is just the number correct over the total. And so this was surprisingly high on the training set, was suspiciously high. And suspiciously is correct because if you remember sort of way back when we looked at a value count and wanted to get an idea of what percentage of the set was class 1 to begin with, found that less than 10% even had that true value. And so if we're being suspicious at this point sort of makes us want to see whether that class balance issue is giving an artificially high score, which, if we plot what the true labels were against what the predicted labels are, we can see that this classifier predicted 0 true values for the entire test set. It only predicted false values. And this is what's giving that artificial score. And accuracy isn't always a great measure of how well a classifier is doing. Usually people, I'll introduce another metric, but if you're interested, this is still a debated issue within data science and machine learning research, like how to correctly evaluate how well a classifier or a model performs on data. But the generally accepted way to measure binary classifiers is using an area under the curve score, or which is represents how well a classifier is able to balance predictions on 2 different classes, how well it's able to not just predict the true class, but also distinguish between the two. Can read, I don't have the tab, but I put in the slide here. A link to some more information about ROC curves, area under the curve, which if you're interested and want to understand what this is, but generally it's a way to evaluate your classifier in a way that more truly represents how well it's distinguishing different classes. So instead of reporting score, take the existing classifier that we trained and see how well it did. And I apologize, I actually added something into this cell. This isn't the existing classifier. I tweaked this logistic regression object to penalize the specific samples in different ways depending on how well they were represented in the initial set. So, the class 1 was about 10% of the total. So when this is learning the proper weights, that B vector for this classifier, it's going to overcount the error for class 1 to try to make it more important for this prediction. And doing that will sort of help it, like, try to force it to predict true labels a little bit more. Balance just means that the relative percentages are in balance with what they were in the training set. And so this 0.5 raw AUC scores go from 0 to 1. 0.5 means that it's still just about random chance. This isn't a great classifier, which what we thought, because the features going into it are really just IDs. They're not super informative. But if we wanted to visualize what it's actually learning, it seems to, I'm going to plot the weight vector, the coefficients of this regression problem against the features. And so this is what these bars mean are basically, it's like before going into the sigmoid, we calculate the sum of the values of each of these features times the corresponding weights. So 0.08 times whatever the value of pre-ICU days were, sum across all of these features, and that should yield the result, the prediction of this classifier. So we can obviously do a lot better. Let me check how I'm doing on time. So I said I would do 840 visualizations. I'm running a little behind, but there should be time to get to that. If anyone ever has any questions, if I didn't explain anything or skipped over anything, feel free to ask, even on Discord afterwards. I'll even give you my email address, but I'll just keep going on, assuming that everyone's with me. So we could do a lot better. These are by no means exhaustive, data munging steps, but it'd be nice to standardize the scales of this input data. And for some models, this does matter quite a bit. So to make the means of each feature vector 0 and unit variance, to put them kind of on the same scales. For logistic regression, it matters more for convergence of the solver, as well as interpretability. So for this bar graph here, it's possible that the teeny bars representing basically 0 weight were actually pretty important, because it could just be that the values of this of those corresponding features are pretty large themselves. So to understand what's really happening, it's nice to standardize the data in some way. Scikit-learn provides a pretty simple way to do that. So I'm just going to create a standard scalar, transform the input data, and that's all I'm changing in this case. And it says it's a teeny bit better. It's still close to random, but better. And that's most likely just due to the how well the solver is able to estimate those particular weights. Next, so going back to my list here, data imputation, which is pretty important because we basically dropped all of the columns earlier. Now let's see if I can do something as sort of broad brush, but maybe a little bit helpful, which is to keep everything, but if a value is not available, then fill it with the median of the column. And Pandas provides an easy way to fill NAs. And I'm going to show you what that looks like. So now we've got a lot more columns. And I'm also going to one-hot encode the string. So now I've got a lot more columns. Train test split, logistic regression, see how well this works. And this standardizing. So the solver didn't reach its convergence criteria within a number of iterations that it wanted to, but we still got a good estimate for what those coefficients that weight vector should be. And it looks like it did pretty much better, which isn't a surprise because we gave it all the data as opposed to only limiting it to a handful of features. And so as you're going through this or iterating, you know, I think a lot of this work is you're building really understanding the data to understand how to better impute missing data, which ones do you remove because they're not important, and you know, unnecessarily complicate what you're doing, add noise to the classifier, etc. Another good part of it is just how to efficiently build, you know, pipelines for training and evaluating these models sort of iteratively. I can show you an example how well a couple other pretty common binary classifiers do. For the sake of time, I'll skip this because all I'm doing is instantiating a couple other classifiers and then printing them. Sorry, and then printing their scores at the end. Thinking about, you know, more clever ways to impute and aggregate data. So before I joined Stony Brook, I spent a couple years as a data scientist, and you know, honestly, a good part of my job after receiving data from a client was figuring out what to do with missing data. And you know, it does require a good understanding of the problem, but you can also do quite a bit by looking at correlations among features to try to determine which ones are unnecessary. You know, for example, here I'm just seeing, are there any features that only have one unique value? So for every single sample, this readmission status is the same. And we should get rid of that because it's unnecessary. For some models, it won't matter. Model may learn to ignore this, but you know, we could probably do much better by selecting these features in a more clever way. There are, of course, algorithms for feature selection. So not everything to be manual, but for the sake of this workshop, I kind of just wanted to introduce you to this library. So hopefully, if you're doing something over the next few days for the hackathon, you wanted to build an easy classifier, I would recommend scikit-learn, PyTorch, Pandas for data frames for tabular data. And this is about the time when I said I wanted to look at visualizations.
Before we go on, somebody has a question about what is imputation?
Oh, I'm sorry. I should have defined that. Imputation, assigning values to missing data. So you can see from like cell 29 here, I'm doing a dot count for every column, and I'm printing this as a percentage of each column that's missing. And you know, some of these are pretty low, but there seems to be quite a bimodal kind of thing where a lot of columns are missing most data. Some columns are only missing a couple percentages. I'm using data imputation as just a kind of a catch-all to represent how to assign values to missing data so that we can handle them in a classifier. There are, I think, one common question regarding this type of work is like, do you need real values for every single cell, for every feature, for every sample? Like, is it possible to, are there models that can handle missing data by themselves? And the answer to that is that it depends on the problem. For this kind of tabular data and regression, we do need every cell to have a value. Every feature for every sample needs to contain something. There are, if you're working with other types of data, other types of classifiers, there or even if you're okay with creating a column that's like, is this feature, does this feature exist or not in the first place, you can kind of get around these issues. So sometimes you just have to try it, and other times you kind of just have to think about the nature of this problem. Like, does it make sense to have a single binary vector in this case that just represents whether the data exists or not, in addition to the actual value if it does exist. Another note on data imputation is like, if you're new to this, I'm pretty sure scikit, has quite a few kind of pre-processing pipelines for handling missing data. Nearest neighbors imputation, so trying to group clusters of the data set to identify similar regions, and then filling the missing data with values from those regions. Other examples. Are there any other questions? If not, I'll go to some visualizations. So as you get sort of familiar with these kinds of problems, data science problems, and these libraries, NumPy, Pandas, you'll also get familiar with matplotlib and Seaborn. These are probably the most common graphing libraries for Python and data analysis. I don't have any examples for, say, Seaborn, but let me show you the example gallery. They sort of make it easy to take an existing data frame, specify the names of the columns that you want plotted against each other, maybe specify a third column by which you want to group data, either color by a different value or plot a histogram. And this library can be pretty helpful for some exploratory analysis. I'm showing here a whole bunch of scatter plots for kind of visually assessing how correlated some data sets are. So, if each variable in this data set is plotted against the other, if it's plotted against itself along the diagonal, then they're showing a histogram. It's pretty common to see these kinds of plots as a part of exploratory data analysis, because it's useful to know for some types of models, for particular linear regression, whether some features are correlated to each other, to another. Ideally, you want uncorrelated features. So I didn't want to spend too much time on this because I thought for the purposes of a hackathon, something like an interactive visualization library may be more helpful if you're considering building apps. So Bokeh is one example. There are many widely used interactive visualization libraries for Python, not for Python. D3 is probably like the ancestor of all of them, if you've heard of d3.js. And I will first introduce this by showing some gallery app examples. this Bouquet allows you to create these types of apps that integrate data in just a couple of lines. This particular one is showing movies, and if any of you are familiar with R and Shiny, this layout will probably look pretty familiar because this is what Shiny looks like. I thought I would show you an example for this data set. So before I'm going to launch this and show you what it looks like, and then I'll come back to this code. But I will, oh, I've already launched it. So I am showing here a very basic interactive in the sense that I can click on it and choose different things, plot that has integrated the data that we've been working with. And all this is a scatter plot with the various features of the data set available. So I can plot one against the other. They want albumin on the x-axis, and where this is, which is a string, so it's going to fail. This should be real valued. Okay, good. And this on the y-axis, the color represents the class. Red means a true class hospital death. The blue is not. And I'm not. This particular example isn't that eye-opening or revolutionary, but if there were particular pairs that I wanted to highlight, where, for example, the red points tended to cluster in one area, that could be a pretty valuable insight for relating how the output relating the output to combinations of these features. This might be helpful for hackathon if I could imagine people taking a stab at a prediction problem and then wanting to create or expose some kind of app that lets someone enter values for those input variables, and then it'll take those in, use an existing trained model to predict an output, and sort of display it for the user. With Bouquet, all I'm doing is calling it. So all I'm really doing is defining an update function. So every time something changes in this app, this update method gets called. I've defined the possible values for this x-axis and the y-axis select elements as all of the columns in data, and this data is just a Pandas data frame. So if you remember from the Kaggle notebook, the columns.toList is just the names of the columns. Those are the possible options. Every time something changes in this page, I get the new selected values from these selects, subset that data frame so that I only have those two columns, and replot. There's there are a lot more fancy things that you can do this, obviously. Different types of source elements, different types of outputs, not just plots. So hopefully this will be helpful. Maybe not this weekend, but just generally presenting generally presenting results from the project like this. That is all I have planned. I wanted to leave some time for you all to maybe go through the data set by yourself. So the data set by yourself, play around with these particular libraries if you wanted to sort of see if you can get some simple apps going. And then I'll be available to help debug or answer any questions. But I hope you got something out of this. And, oh, forgot my slides. I have some ending slides. Data set ideas. I know this is the start of it, so if you wanted to do something related to data science analytics, machine learning challenge, here's some suggestions for data sets. This is, you can literally Google open data sets and find, all sorts of curated lists, but these are a few that I know of that are related to healthcare. Kaggle healthcare challenges. This year's Women in Data Science Datathon is going on right now, and I think it closes in March. So you can, January 6th to March 1st. So if you wanted to participate in this as well, I think you have to fill out this form before being able to enter the Kaggle challenge. But it seems pretty interesting. It uses the same data set, but just predicting something else. PhysioNet, as I mentioned earlier, has plenty of data sets with real world physiological data. And then for data science help, I really like the Kaggle micro courses, especially for getting started or rehashing some skills. I've put this cookie cutter data science repo here, which is a suggested file structure for handling your work, because it's really easy to get lost with 10 random Jupyter notebooks, and then your data is also in the same folder as everything else, and you're never sure which is the current most recent version of the model. But hopefully this shows it here. Yeah, this is a pretty well accepted structure for data science projects. You put your raw data that you get in one folder and never touch it. You can, when you process, you can then copy that data and store it in another folder so that you're sure you're not overwriting things. Jupyter notebooks in a separate notebook dated in a particular way if you understand what's going on. And this makes it easier to source control your stuff too. And then, of course, an awesome data science list if you wanted any more suggestions or inspiration. Now I'll be around, and please let me know if you're tackling anything handles big data or looking at any data science challenges.
Yeah, thank you so much for hosting this workshop.
Yeah, of course, thank you. I hope, also, please don't hesitate to reach out to me if you're still in the audience with feedback if there's, anything you wanted to learn more about. I'll be around.
Yeah, okay. I'm gonna end the stream now.
Cool. Thank you.